Hi there. After understanding the dynamic stability of the equal real roots, now we will do the same for the complex roots. And for that, we remember that the general solution of the second order differential equation was this, and it has a complementary function which shows the deviation. This is the particular integral which has these three possibilities of the equilibrium value. So we focus on the deviation, which is the complementary function. We chalk it out and we see that it has two major parts. One is this multiplier and the other term is the multiplicand. So we want to reduce this deviation, and now we are going to split this into its two parts, the multiplier and the multiplicand. When we consider the multiplier, it is actually an exponential function which has h as the rate of growth, and when we talk about the other part, the multiplicand, it has an arbitrary constant, then a trigonometric ratio, and it includes the variable t. The other part in the multiplicand is the arbitrary constant and then the trigonometric ratio. So these are the two parts. Now this diagram is plotted just below this part, that is the multiplicand, because when we have such a function that has cos theta and sin theta, instead of theta we have vt, and we have vt with the sine trigonometric ratio as well. So when we have such a situation, we have a wave-like motion of the graph. As you can see, it's a wave-like motion of the graph. So this is to be analyzed, because this movement of the time path will guide us if there is equilibrium, desirable situation, that is convergence, or the equilibrium undesirable situation, which is the divergence. And another possibility is there that we will see, that is we have an uniform oscillation, because this is oscillation below the x-axis and above the x-axis, above, below, above, below. So there is oscillation, we can call it oscillation, and it is entering the positive area and the negative area continuously, alternatively. It is having this situation. This is the multiplicand, and it has a wave-like graph, and it right now it has the uniform amplitude or the uniform oscillation, but the third possibility is also the same, that is the wave-like motion will remain the same. Actually there will be three possibilities, that is convergence, divergence, and the third one is uniform amplitude or uniform oscillation. How all these possibilities can take place, it quite a bit depends upon the multiplier, which is actually an exponential function, because these terms, they are basically arbitrary constants a5 and a6. Sine and cos theta, instead of theta we have v and t. So this is a value that is beyond our control, that is it will start from 0 and it can go anywhere close to infinity. So this h seems to be the value that can make a difference, because it is in the exponential decay expression, and in this expression, if the decay happens, it is going to eat away this multiplicand and there will be convergence. So focusing on the multiplier, as this approaches to 0, as time goes on, we can achieve the desirable situation of convergence, and that will happen if the amplitude is mitigated. So let us see, with the help of this numerical example, we are basing our analysis on the value of h, which is here. In this case, we are assuming that the value of h is 1. In this case, we are assuming that the value of h is 0, and in this case we are assuming that the value of h is -1. So there are three columns that we will analyze here. Here we have used 1, so let us solve this. We are decomposing the YC complementary function into its multiplier part and the multiplicand part. The multiplicand part will have this series of values once we put the value of t starting from 0 going to 10, and this series of values is showing alternative signs, as you can see, plus, minus, plus, minus, minus, plus, minus, minus, plus. You see quite a bit of alternative trend of the signs it appears. It verifies that what we saw a little while earlier in the diagram, that a wave-like motion will appear. That is, we will be in first quadrant, and then will be fourth quadrant, first quadrant, fourth quadrant, fourth quadrant, and then first quadrant. Yes, we can go into the second and third quadrants as well, but let us assume that we are talking about these two quadrants. Bottom line is that we will have a wave-like motion as the sign is switching. Then we have this series of values generated as we put various values of t. H, we assumed it as 1. So you see that this value is increasing when we use 1 as the value of h. When we add these two components of yc, we get 1, and then we get various values here. Then you can clearly see that yc is increasing, which is undesirable, and it shows that we have dynamic stability is unlikely. Let us just go ahead, and then we will compare all the terms that that appear once we do this analysis. So let's come to the solution part first. Here h is equal to 0, and these are the two parts that we have of yc. So this is the first part. As we consider h is equal to 0, all of the answers will be equal to 1, because the part that is the exponent, it will be 0, so the answer will be equal to 1. This is again the same expression as we saw before. This series of values is going to be the same based upon the same expression, this multiplicand part. When we add these two values, we get a series of values, and we have to consider that how these various values are changing. It starts from positive, turns negative, positive, negative, and it changes sign, and then 1.6 is there as the final value. So these are the values of the complementary function for the second case where h is equal to 0. Finally, we compare these two results with this final possibility, that is h is equal to -1. So this expression will be evaluated. You will see that these will be the results. This value is declining. It shows that there is exponential decay, something which is desirable. This is the multiplicand part, and it is having the same set of values, and then we find the overall value. This is not the sum, this is product. Here again it is product, here again it is product. So if I have said somewhere that it is a sum, then it was not correct. It should be a product, because these two terms are being multiplied in the formula of complementary function. So this is 1 into 1, it is equal to 1, and then we will multiply and we will get this, and for example these two terms getting multiplied equal to this. Now once we have found these, the pattern needs to be observed. This is the first value, and this is the final value in this range that we have observed. It started with a positive value, and still it is a positive value. The other thing is that the value has increased very much. It started with positive 1, and it is reaching 34,546. So it means that there is a movement which is showing increasing deviation, and substantial increase in deviation is there. Moreover, in this process of oscillation, the first negative value is minus 7.9 and the final negative value is 25,146. So it means that the negative value is also having this substantial increase in terms of its magnitude. So it means that the oscillation is increasing no matter we are above x-axis or below x-axis. Above x-axis there are these positive values and below x-axis there are these negative values. So we can say that the exponential expression is having a growth here. The multiplicand part is increasing and decreasing, that is having positive and negative signs, and the complementary function is also there. It is also changing signs, but on the whole it is increasing because the value in absolute terms it is increasing. Now the other case where h was equal to 0, the value of the multiplier it is constant, so we have a bar on it. The nature of the multiplicand is the same, and the nature of the complementary function it is also similar because plus and minus signs they are happening here. But this case is slightly different because if you focus on it, because it shows that there is no substantial increase. Actually it started with 1 and it is here 1.6, so it hasn't changed much, and in the middle there are two highest values positive in positive sense, that is 3.1 and 3.1. so these two values are the same. It means that the values they are coming back to their previous levels, because after this 3.1 it becomes negative, remains negative, then becomes positive, and then becomes the same value. So it means that we are having the repetition of those values. It means that it is having a format which is uniform. We will see this as we go ahead, but here again let's complete this, and this shows that the exponential decay is happening as the value is declining as the time goes. This is the same as we had before, and the final result is showing that the value is declining on the whole, because we started with 1 and now we have a value which is nearly equal to 0. When we consider the negative values, the first negative value was minus 1.07 and now it has declined as well. So it means that the decline is there no matter we talk about the positive values or the negative values. It means that the deviation is on the decline in absolute terms. So here we see plus and minus signs they are occurring, but this value is declining. So this is the result. This is the term that we can use here. There is explosion here because the value it is increasing no matter negative or positive. So it's an explosive pattern that we have here. The pattern here was not explosive, it was returning back to its original values, that is 3.1 and 3.1. There will be other same values as we use greater values of t, that is values beyond 10. So we can say that it's a uniform oscillation because the time path is coming back to its previous values. And here there is damped fluctuation because it is getting dimmer as we go ahead in time. The absolute value it is declining and approaching to 0. So the first one is explosive. It means that the deviation is increasing in an explosive manner, and the explosive fluctuation will lead to divergence. Here the uniform oscillations are the result of this expression, and it means that it is neither moving away or nor moving close to the equilibrium. It is having the same distance from the x-axis and it is not changing its amplitude. So it will neither cause divergence nor convergence. We will see these diagrammatically as well. Finally, the damped fluctuation is happening as we see that the value is declining as we go ahead, and definitely it means that the deviation is dampening or decreasing, and we will have convergence. So let's consider these in this diagram. You can see in the first example, no matter we are before or after the y-axis, the movement is oscillatory, and above equilibrium, below equilibrium, this pattern is happening. Above equilibrium it will be positive, and below equilibrium it will be negative. So it is an explosive movement, because you can see it is moving further and further from the middle point. It means that it is having an increasing amplitude, explosive manner it is. So it's not going to converge towards the equilibrium. Here we can see that plus minus both of the values are occurring, but it is having the same amplitude, same distance from the x-axis above and below the x-axis. This means that it is neither going to cause a convergence towards the equilibrium nor divergence from or away from the equilibrium value. Now finally, there is this possibility where the deviation is decreasing as we go ahead. This oscillation is having a smaller amplitude as we go ahead. So this smaller amplitude means that we are getting close to the equilibrium. So this is dynamically stable. The previous one was neither dynamically stable or nor dynamically unstable. So the condition is that h should be negative, because this is the case where h is negative, h is 0 and h is positive. So it should be negative. The value of h negative shows that we can have convergence. With the help of this numerical, we understood this, and this was the understanding of this wave-like motion, which is a consequence of trigonometric functions in the complementary function. And this is the final case of the dynamic stability of the complex root case in the second order differential equation.